So we've got negative x cubed. Make sure you get that negative sign. Negative x cubed plus 12x plus 5. Now, sometimes students, they're kind of ready to do this on their own. I don't want you to get nervous if you're like, nah, I'm not sure I'm ready, but you can do the derivative. You already can do the derivative. You can set it equal to 0. I guess I'm kind of wondering if you think you can do the number line, even though we only did one problem yesterday. I'll just be a step behind you if you're thinking about doing some of this on your own. Right now, we're just doing mainly what you did on the quiz yesterday. Please know that when you solve this equation, you're solving it for the critical points, okay? Because critical points always occur when a slope is equal to 0. Same thing that we did, again, in the last section. Now, the answers that you get to this, you would put on a number line. So if you're thinking about doing that, keep going. The answers you get to this, you're going to put on a number line. Make sure that you get 2 answers. That's a big deal because if you miss the plus or minus, honestly, your number line will not be divided correctly. And that's exactly what's going on here. When you put these 2 numbers on the number line, you're actually dividing it up. You're segmenting it into 3 sort of spaces, 3 intervals. And what you're going to come to realize is that whatever happens in this interval at maybe the number -3 is going to happen everywhere in that interval. Whatever happens in this interval, like maybe the number 0, we said that if you can, pick it. And whatever happens in this interval, say at 3, well, again, it's going to happen everywhere in that space. Now, you should be taking those yellow numbers and plugging them into the derivative. Plugging them into the derivative. This is not a bad exercise to try to do without a calculator. I don't care if you're using one, but eventually you'll do this without a calculator. You're just squaring and multiplying by -3 and then adding 12. What does this mean to get some of these outputs? What does this really mean? By the way, if you have a question, please ask. Okay, you guys are here. We can take care of what you need. Again, I'm just squaring numbers, multiplying by -3 and adding 12. You happen to get these values, but what really matters is the positivity or the negativity. What really matters is if it's positive or negative. In fact, I will have students just summarize, not even show -15, they'll just say negative. I actually will start to do that myself because I don't really care if it's -15, I just care that it's negative. I don't care if it's just 12, I just care that it's positive. Because that means that everywhere in those spaces, you have that kind of slope. Are you picturing something? Are you picturing a graph that goes down? That's kind of my way of saying that's what you want to do. Can you picture a graph then that goes up and then goes back down? Do you want to draw it? Are you able to use that to help you get the max and min? Are you able to also use that to help you get the increasing, decreasing? That's kind of what our goal is. So picture it. Can you picture a graph that goes down? And then a graph that goes up. And then a graph that goes back down. Now, sometimes people aren't confident because this is new. So you're like, well, how'd you know to draw it just like that? Really, it doesn't so much matter how curvy it is. It just matters that you picture going down and then back up, because that has to be a minimum. And again, that's the whole new idea yesterday. That's why you came to class, so that we can say that -2, and may I say kind of the official way, is to say that -2 is a minimum because the slope was negative and then it was positive. Okay, no more do I kind of just have to like make a guess or some other strategy. And obviously 2 is a maximum. 2 is a maximum for the opposite reason. Okay, and then we can give a little increasing, decreasing. Increasing just means the slope is positive. I want you to realize that we already figured that out. Based on the number line, the slope is positive between -2 and 2. So that's the same thing we figured out when we put this plus sign here between -2 and 2. Then, of course, it's decreasing in the other spaces. And if you want to use interval notation, you can use -infinity, positive infinity. There's kind of one missing piece here. It's sometimes the piece that's kind of a pain in the butt. And it's also sometimes the piece that I say, you don't need to do it. But then sometimes we say you do need to do it. It's the y value. Now, the y value is found by plugging back into the original equation. And it's kind of a pain because, it's just some more computation. But it is part of like a final complete answer. If you have a calculator, so like on a test, if you have a calculator, you're going to be finding these y values. So if I plug 2 back in here and I cube it and multiply it by 12, you get 21. And you also get -11 if you plug in -2. Make sure you just realize how I did that. I just plugged back in. How about the graph of the derivative? The same thing that we began the class period with. How about the graph of -3x squared plus 12? Now again, if you're really trying to figure this out, maybe you're already picturing that graph. But if you're like, this is a little bit, this is a little fancy, it is. So just take a deep breath and let's talk about it. The graph of -3x squared plus 12, the graph of the derivative. Eventually, you won't be surprised by what you see here. So first off, that's not the graph that I drew, okay? Because the graph that I drew is an x cubed graph. This is the derivative graph. This is a x squared graph. But really, when it comes down to it, this graph is saying something to us. And I get a feeling that you're hearing it. That is, if you realize that it's simply saying to us that there's some positive values. Look, I don't really care that the graph is turning or curving. I just care that it's positive. And when you have positive values, you have positive slope. That's the same as the positive slope that was shown right here. Now that's kind of neat if you make that connection with me, that this arch right here, this arch is actually referring to this S-curve, this positive slope. And then in kind of the opposite manner, these negative values are referring to these negative slopes. And these negative slopes, of course, are going down. So it's not far out there for us to say that this graph is saying the same thing that we have up here. It looks different, but it's saying the same thing. And we notice, I hope one more time, that the x-intercepts are the critical places. They're the places where the positive and negative changes. And yes, this has physics written all over it. Right now, we're just trying to focus on the slope part, try to keep it, sort of just keep it true to that. But we will go to the physics part as part of this chapter. Now, can I just kind of be honest with you? The two problems that you see up here from yesterday and today, they're kind of like the normal. Like, you know, you get stuff that goes up and it goes down, and it's kind of normal. What we're going to spend the rest of the time with are problems that they have something, I guess, abnormal, or maybe just not what you might have expected. And this is where we start to try to take what we're learning and apply it to like a new situation. And let's try one. All right, so what I have here is the function e to the negative 0.5x from -1 to 4. So we have this extra statement tacked on here. We have this basically this interval. If I could also say, when you guys get a problem like this, like in your assignment, and this is the way this class works, I try to show you things and then you do it in your assignment. When you get to something like this in your assignment, you want to go through these steps. Don't just graph it on your calculator. Don't just look in the solution manual. Think about these steps. Okay, because if you think about them, you'll start making the connections. If you just kind of skip over the thinking, then you might not realize what the calculus is really saying. Now, it's an e to the x, so that's fun. The derivative is the same, of course, times the derivative of the inside. So when we multiply by the derivative of the inside, we're actually going to get a little -1/2 in front of our e to the -1/2x. So I'm doing the derivative and the chain rule all in one step there. All right, so that's our derivative. You're supposed to set this thing equal to 0. So we'll, like a good little boy or girl, we'll set it equal to 0 and try to solve this. Now, when you solve this, you could use a calculator, kind of expecting that you would be using a calculator at this time. But just think a little bit about the algebra. Divide the -1/2. Oh, it just kind of divides away. Take the log of both sides. And I wouldn't so much say that this is it's just equal to, but you realize, again, with a calculator that you can't do that. There is no value for the log of 0. Now, what this means is that there's no critical point. There's no critical point. But this is the part of the problem where we want to be careful about what this doesn't mean. You see, it doesn't mean that there's no number line. And it certainly doesn't mean that there's no slope. It just means that there's no place where the slope is going to change. Now, what I just said right there is pretty significant. So just process that with me again, because sometimes students will just say undefined and sort of just move on. But how silly would that be to say that this function is somehow like undefined? No, this is a function. It's a graph. It just doesn't change. There's no place where the slope changes. Now, thankfully, we have some endpoints that kind of give us something to think about. And when you have endpoints, they show up on the number line. That's kind of new. So I'm putting them on there. And hey, there's numbers in this number line, like any number you want between -1 and 4. What number do you want? I suggest picking 0, but 0 sometimes can be a little tricky, especially when a problem like this is already kind of strange. But I'm going to pick it because I want you to see that we can actually plug 0 into the derivative. Now, when you plug 0 into the derivative, you get e to the 0. So when you plug 0 into the derivative, now remember, I'm plugging into the derivative, which is this version. There might be a professor in college, if you take calculus, that won't let you use a calculator. So I'm trying to also guide you like this. So e to the 0 should be some knowledge that you've obtained in high school. E to the 0 is 1. 1 times a negative number. 1 times a negative number. It's negative. It's negative. You can write -1/2, but the conclusion is that it's negative. Now here's sort of the crux of the problem. But I don't want to just say it. I want you to think about it. This is the slope between -1 and 4. It's the slope of the function. So what's the function look like? What's the function look like? And where's the max or mins? Sorry, the bell kind of got in the way there. This is the slope. Are you picturing a graph that has that slope? So what's it look like? And what's that mean for -1 and 4? Where's the max and mins? Well, we're a friendly crowd. What's the graph look like? If it has a negative slope, then the graph is always going. What would be negative? The slope would be negative. So the graph is always going down. What's a graph that's always going down? Now, I've seen a few graphs in my lifetime, but I want you guys to start to get comfortable with them. So the graph that I just drew, it's going down. It also has a little curve to it because honestly, e to the -x is an exponential decay. Oh, wait, exponential decay. My algebra teacher told me that that's always going down. Your calculus teacher, well, I didn't tell you. The slope told you that it's always going down. So what's that mean for our endpoints? Well, it's kind of like almost too easy. I hope that you would say this one has to be the maximum. Okay, this one's the maximum. And, well, this one's the minimum. What I'm trying to get you to realize is that the slope says it all. It really is the king around here. The slope says it all. It told us that the graph looks like this. It also told us about max and mins. And it helps us to kind of fill in our little chart. But I'm basically just kind of copying down the conclusions that we made. So there's a maximum at -1, there's a minimum at 4. It's never increasing. That's because the slope's never positive, and it's basically always decreasing, but technically between -1 and 4, because that's all we have. How about these y values? As I said, honestly, sometimes they're a pain, but I could plug -1 in here, and I could get e to the 1/2, and that is an appropriate way to give an answer. You can give it in terms of a function. So I plug in -1, and I kind of like circumvent the calculator. I plug in 4, and it's the same thing. If you plug in 4, you get e to the negative 2. Maybe we should write that as 1 over e squared, but again, I'm basically trying to show you that we don't need the calculator. Do I have 30 seconds or like a minute and 30 seconds? A minute? Well, let's see what happens, because I don't want to forget it this time. What are we going to do here? We're going to graph the derivative. What do we expect to see? This is some deep stuff here. So you can kind of do two things right now. You can just kind of wait, or you can think a little bit. What do we expect to see? It's a different problem, so it's kind of interesting. Now we expect to see the slope, right? What kind of slopes? Negative slopes. But what that really means is we're going to see negative values. And when you look at that, all the values are negative. It's a little harder, but if I show you that graph, we could eventually come up with the graph we did behind the screen, because that's all negative values, which means negative slopes, which means the graph's always going down, which is the exponential decay that we graphed again in this example.